So you could have a count. I think I'm recording now. Good. Okay, so you could have countably infinite sample space, but it's still discrete, right? So A is false. B, the probability density function of a continuous random variable is the function little f of x equals capital P of capital X equals little x, right? So that's true. You still use a PDF for a continuous random variable. It's just that this, oh, no, so sorry, it's false. The probability of, yeah, no, so this is true, right? So the PDF is that, except this probability is 0, right? So f of little f of x is 0. It's still true, this equation, except when you want positive probabilities, you're going to want to take a probability of an interval, not just a single specific value of x, right? So B is true. Okay. C, it says if the probability capital X equals little x is 0 for all possible values x of a random variable, then x cannot be a discrete random variable. Well, that's true, right? So if x was a discrete random variable, right, then you would want you would need some positive probability for some point x, right? If you look at the contrapositive of this statement, if you think of x as a discrete random variable, right, you couldn't possibly have that the probability of every sample point was 0, right? You would need something to have positive probability. Only for a continuous random variable could that happen. So C is true. C is true. And D, if f of x is the probability density function of x, then this probability is equal to the integral of that function. That's true. That's how you compute probabilities. Oh no. Okay, sorry. This is false, because this is only true for a continuous random variable, right? If you have a discrete random variable, you wouldn't take the integral, you would take the sum. Okay? This is how you compute probabilities for a continuous random variable, not a discrete one. Okay, so D is false, A is false, B and C are true. Okay, so since there weren't any questions, I just answered that one. Okay, so
I have a question.
Okay, yeah.
It's actually hold on. It's 5.5, number 1.
Okay, good question. Okay, so let capital F of x equal to this piecewise function be the cumulative distribution function of the random variable x. Find each of these probabilities. Okay, so I'm going to copy this. So this is 5.5, number 1. Never mind. Okay, so that's not going to want to copy and paste. So let's just go back to it. All right, you can see that there. Okay, good. So so you want to find the probability that x is less than or equal to 1. Right? So the probability that x is less than or equal to -1 is equal to the integral from -infinity to -1 of oh wait. Okay, so the probability that x is less or equal to -1 is equal to capital F of -1. That's what the definition of capital F of -1 means, right? And so capital F of -1 is well, where is -1? -1 is in this interval, right? -1 is an x value less or equal to 0. And so the value of capital F is 0. Does that make sense?
Yes.
Okay, good. Okay, so so for that one, The answer is just 0. Okay. So the next one, that's good. So the next one is the probability x is less or equal to 0.5. That's just capital F of 0.5, right? And so capital F of 0.5, 0.5 falls in this interval. And so you just plug in x squared. So this is 0.5 squared, or 1/2 squared. That's 0.25. That makes sense?
Yes.
Right? Because capital F of x as a cumulative distribution function is the probability that your random variable capital X is less than or equal to little x. And so when you have these numbers here, you just plug them in here, right? And so capital F of 0.5 is the probability x is less or equal to 0.5. Okay, so okay, so we did this one, we did this one and this one. And so there's this one. Probability x is less or equal to 0.3. So Cesar, what is the probability that x is less or equal to 0.3?
Would it be 1? Oh wait,
No,
no, I'm
look,
sorry.
the probability that x is less or equal to 0.3, right?
Yeah.
That's equal to capital F of blank. What do you put in the blank?
Will we put the x squared?
Well, read this for me. Read that equation for me.
Yeah, f of x is equal to the probability of x is less than or equal to x.
Good. Okay, it's capital F of x, right? Capital F of
Yeah.
little x is equal to the probability that capital X is less or equal to little x. Could you say all that with the capital and lower letters?
Yeah, capital F of x is equal to probability of capital X is less than or equal to lowercase x.
Yeah, little x. Good. So this lowercase x is the thing that's in the parentheses here, right? So
Right.
what is the probability that capital X is less or equal to little x equals 0.3? It's capital F of what?
I'm not sure.
Okay, well, you see the little x in the parentheses there?
Yeah,
Where does it go over here?
in the little x.
Right. So in this equation, what is the box in the other equation?
So would it be 0.3 as well?
Exactly. Good. So you put a 0.3 there. Okay.
Right.
So does that make sense?
Yes.
Okay. So what's capital F of 0.3?
Capital F of 0.3. So wait, for the capital F, what are we plugging in though?
There's capital F, right? So which interval is 0.3 in? The first, second, or third?
The second one.
Good. Okay. So then what is capital F of x there?
F of x is, would it be a 0.3 squared?
Good. Okay. So now if you take 0.3 and you square it, what do you get?
0.09.
There you go. And that's the answer. Does that make sense?
Yeah.
Okay, good. Okay, good. Okay, so what is the probability that x is greater than 0.4?
Would we do it like the same way? So plug in for
Almost. See how this is less or equal to? This is greater.
Yeah. Right. So since it's greater than, would we still be using the x squared, or would it be just 1?
So 0.4, right? Which interval is 0.4 in? Is it in the first, second, or third interval?
It's still in the second.
Good, right? It's in this one, right?
Yeah.
So we're looking at this probability here. So the probability that x is greater than 0.4, though, it's equal to 1 minus the probability that x is less than or equal to 0.4. Does that make sense?
Yes.
Because they're complements of each other. This purple statement is the complement of that statement. They're complements of each other. Right? When two events are complements, it means that one is the negation of the other. Right? The negation of x greater than 0.4 is x less or equal to 0.4, right?
Yeah.
And same vice versa. The negation of x less or equal to 0.4 is x is greater than 0.4. The probability of an event A is equal to 1 minus the probability of A complement. Right? So probably x is greater than 0.4 is equal to 1 minus probably x less or equal to 0.4. So that's equal to 1 minus, and then what goes here?
Would it be 0.4 squared?
Yeah, exactly.
So it's 0.16,
Good. So what's 1 minus 0.16?
0.84.
There you go. And that's the answer. Okay, so that makes sense, right?
Yes.
Okay, and now the last one, what is the probability that x is greater than 0.2 but less than or equal to 0.5?
Are we still using the second row because 0.2 and 0.5 are still like in that middle section?
Exactly. So they're both in that interval, right? But now you want to express, before you use that function, you want to express this probability as a difference of two probabilities. Can you see how to do that? Okay, so let's say I put the probability that x is less or equal to 0.5 here, right?
Right.
What would I put in the other one?
The probability that x is greater than 0.2.
Almost, but there's a minus sign here. You're subtracting this probability, not adding it.
So it'll be less than.
I'm going to write less than or equal to, but yeah, that to what?
0.2.
0.2, good. Does that make sense?
Yeah.
Okay, if you have a number line and you want to find all the numbers that are greater than 0.2 and less than or equal to 0.5, then you're on this purple interval here, right?
Right.
Okay, so instead of looking at that, you can say, well, what are all the numbers that are at most 0.5, this red part, right? And then subtract from that this blue part, all the things that are less than or equal to 0.2. The probability of the red part minus the probability of the blue part is the probability of the purple part.
Yeah.
Does that make sense?
Yes. So we just plug in for the x squared for x less than or equal to 0.5.
Yeah, so it's 0.5 squared, right? And then minus what?
Yeah, minus 0.2 squared.
Good. Okay, so what's 0.5 squared minus 0.2 squared?
0.25 minus 0.04.
Which is what?
That's 0.21.
Good. There you go. Okay, so it makes more sense, right?
Yeah.
Okay, good. Okay, so then that's that explains that problem. Okay. If
Yeah.
you want more help, I have office hours every Friday, so I can help you more there too. Okay, so anyone have any other questions about the homework? Okay, good. Okay, we have a lot to do. So let's go back to here. Actually, before we start, let's just review the last lesson. Okay, so we started our talk on wait, something's messed up about my screen here. Lesson 18. Okay, so sorry, the Zoom is, I think it's acting up. There we go. I got it. Okay, so lesson 18, we started with cumulative distribution functions of continuous random variables. So here we gave the definition of a cumulative distribution function, right? It's this integral here. We had an example where we computed values of it. We found the CDF in this example, and we sketched its graph, okay, by cases. We talked about properties of a probability density and cumulative distribution function. So we talked about properties. We talked about the continuous uniform distribution. Okay, we had an example using it. We talked about the exponential distribution. So this is going fast, but so we did last time. Okay, and this is the exponential probability density function. Okay. So today, I'm just going to keep going. It's kind of a new idea here. So random variables that satisfy either of the following two properties, two conditions, are exponential random variables. Okay. So just to start going back and forth, this is the definition of an exponential random variable. I'm going to copy and paste it here. Okay. Okay. So that's an exponential random variable. It's a PDF of this form. And it's with parameter theta. So if you have a different theta here, it's a different exponential probability density function. Random variables that satisfy either of the following two conditions are exponential random variables. So one, if the random variable x sub t that represents the total number of occurrences of the phenomenon from time 0 to any given time t is a Poisson random variable with parameter lambda t. Sorry, so if that happens, then the waiting time until the first occurrence is an exponential random variable with parameter theta equals 1 divided by lambda. So if the random variable x sub t that represents the total number of occurrences of the phenomenon from time 0 to any given time t is a Poisson random variable with parameter lambda t, then the waiting time until the first occurrence is an exponential random variable with parameter theta equals 1 over lambda. Okay, so that's 1. 2, if t is any non-negative random variable that is memoryless, meaning that the probability that t is greater than s plus t, such given that capital T is greater than little t, is equal to the probability that capital T is greater than little s. And this is for all s and t non-negative. If that happens, then capital T is an exponential random variable. Okay, so the conclusions of both 1 and 2 is that you have an exponential random variable. Okay. For 2, the assumption is that, well, if t is any non-negative random variable that is memoryless, meaning this property, that the probability that t is greater than s plus t, given that t is greater than little t, is equal to the probability that t is greater than s for all st non-negative. Okay, so to illustrate these things, let's look at this example. So example 5.12. Suppose the number of automobile accidents from time 0 to time t in hours along a segment of highway Z is a Poisson random variable with parameter lambda t, which is equal to 1/15 t. Furthermore, suppose there is an accident there at 10 a.m. A, find the probability that there will not be another car accident along this segment of highway for at least 24 hours. Okay, so let's look at, this is property 1 here. So when we're looking at this problem, we want to look at property 1. So A is corresponding with property 1 there. Okay. So let T be the time in hours until the next accident occurs along this segment of highway. Okay, so T is the time in hours until the next accident. We want to find the probability that there will not be another car accident for at least 24 hours. So what we want to find, the probability that there will not be another accident for at least 24 hours. Well, that's equal to the probability that T is greater than 24. Okay, T is the amount of time you have to wait for the next accident. So we want to find the probability that there's not another accident for at least 24 hours. That means that it's probably T is greater than 24. Okay, and so adding or removing the equals 24, it doesn't change probability. So probability T is greater than 24, and it's equal to the integral from 24 to infinity of our probability function. Okay, and so our probability function f of x dx. So here, little f of x is our probability function. It's saying that we have a Poisson random variable with parameter lambda t equals 1 over 15t, right? So that's telling you the distribution function. Okay, that's telling you the little f of x. Okay, so then what is little f of x? So little f of x is just equal to 1 over 15 times e raised to the negative x divided by 15 as a Poisson random variable. Or since capital X, capital Z is a Poisson random variable. Okay, so t, I'm using t for time. So I guess let's go with dt. Okay, so f of t. It's highway z. Okay. Okay, so then that's so that's the probability density function because it's a Poisson random variable. Okay, good. So then you just integrate this. So then this is equal to this integral times f of t, which is this function right here, 1 over 15 e raised to the negative t divided by 15 dt. So that you just use the PDF there in the integrand. And so when you integrate that, you get e raised to the negative 24 over 15. Okay. How you get that? So Okay, so and that number as a decimal is approximately rounded is 0.2019. Okay. And if you want to, how do you find this integral? You use substitution, right? So this is calculus. So if you have this integral, right, you want to use substitution. So okay, so using u substitution, where u is equal to negative 1/15 t, we get du is equal to negative 1/15 dt, and that this integral is equal to, well, the 1/15 here, we're missing a negative. So what we want to do is just introduce a negative sign. So we have a negative here, and we're going to have a negative here. So if you put the negative here, you now have a negative 1/15 dt here for the du, and you have a u for the negative 1/15 t here. So by u substitution, this is equal to the negative of the integral from the integral of e to the u du, right? Because I'm substituting negative t over 15 for u. I'm substituting negative 1/15 dt for du. And then when x is 24, and when t is 24, then u is negative 24 over 15. And when t is infinity, u is negative infinity. Okay. And so then this is equal to, you switch the limits of integration when you get rid of the negative sign. So the negative infinity goes here. Negative infinity goes here. Negative 24 divided by 15 goes here. I get rid of the negative sign, and it's e to the u du. The antiderivative of e to the u is e to the u, and antiderivative. And so you evaluate that from the lower limit to the upper limit. And so then this is equal to e raised to the negative 24 over 15 minus e to the negative infinity. And so that's equal to e to the negative 24 over 15 minus 0, okay, which is e raised to negative 24 over 15. And that's the answer. And so that's how we get from that integral is equal to e to negative 24 over 15. Okay. Okay, so then that's part A. Find the probability that there will not be another accident for at least 24 hours. So the probability t is greater than 24, which is the integral from 24 to infinity of the PDF of the Poisson random variable, 1/15 times e to negative 2 over 50. Okay. So that's part A. Part B is find the probability that there will be another accident on the same day. Okay, so what is the probability that there will be another accident on the same day? So remember that t, as we defined it, is equal to the time, in hours until the next accident occurs along this highway, right? So then, so remember from A that we have t already. Okay. So that's how long it takes for the next accident. We want the probability that there will be another accident on the same day. Well, then that means that the you want to find the probability that the amount of time you wait until the next accident is at most 24 hours. It's time in hours, right? So the time in hours. So you have to specify the unit of measurement. So it's in hours, and so you want to wait almost 24 hours. Probably t is lesser than 24. So this is equal to the integral from 0 hours waiting to 24 hours waiting of the same PDF function. So our PDF function is 1/15 e to negative t over 15. So now you're just using, now you're calculating that integral. Okay, and this is equal to, without calculating though, you know this is 1 minus the probability that t is greater than 24. Because just like in the homework example, this is the probability of the complement of that event, right? If t is not less or equal to 24, t is greater than 24. And we already calculated this probability in part A. The probability that t is greater than 24 is e to negative 24 over 15. So this is equal to 1 minus that. And so this is equal to 1 minus 0.2019. It's that decimal from part A. So this is equal to 0.7981. All right. And so then that's the answer. Okay, any questions about that example? Okay, so here's another example. So example 5.13. Suppose an electrical system is maintained very well, so it makes sense to assume, so get that blue. We're doing this now. Okay, so property 1 is going to be now. Sorry. Okay, so it makes sense to assume that the system will not fail for at least s plus t hours, given it has not failed for at least t hours. Okay, suppose an electrical system is maintained very well, so it makes sense to assume that the system will not fail for at least s plus t hours, given it has not failed for at least t hours, is the same as the chances it will not fail for at least s hours. Okay. Also, suppose probability it will not fail for at least 10 hours is 0.99. Find the probability it will not fail for at least 100 hours. Okay, so here's a full example. Suppose an electrical system is maintained very well, so it makes sense to assume that the system will not fail for at least s plus t hours, given it has not failed for at least t hours. So that the probability that the system will not fail for at least s plus t hours, given it has not failed for at least t hours, is the same as the probability it will not fail for at least s hours. Okay. Also, suppose the probability it will not fail for at least 10 hours is 0.99. Find the probability it will not fail for at least 100 hours. Okay. The probability that the system will not fail for at least s plus t hours, given it does not fail for at least t hours, is the same as the probability not fail for at least s hours. This statement right here is this here. Wait, it's this blue statement here. Sorry, it's blue. Okay, so we have blue. Okay, so the probability that the system will not fail for at least s plus t hours, given it has not failed for at least t hours, it's this one. Okay, this one. Okay, so property 2 says that if this equation holds, then t is an exponential random variable. No, well, let me say my thing. So if this equation holds, then it's an exponential random variable. This is the equation from before. So property 2 says that if the following equation holds, then you have an exponential random variable. Okay, so the probability that the system will not fail for at least s plus t hours, that's this. The probability that the system will not fail for at least s plus t hours, let me change the color again, is this thing right here. Okay, the probability that the system will not fail for at least s plus t hours, given it has not failed for at least t hours. Given it has not failed for at least t hours, is the same as the probability it will not fail for at least s hours. Okay, so I'm using a lot of colors here. Okay, the probability that the system will not fail for at least s plus t hours, given that it has not failed for at least t hours, is the same as. So this is the same as part is the blue part right here, as the probability that it will not fail for at least s hours. That's an actual statement. Okay, so this equation is that sentence right there. Also suppose that the probability it will not fail for at least s hours is 0.99. So it's saying that the probability, t is the amount of time before the system fails, right? T is going to equal the time in hours until failure in the system. Okay. So the probability that t is greater or equal to 10 is equal to 0.99. So the probability will not fail for at least 10 hours is 0.99. And the goal is to find the probability that it will not fail for at least 100 hours. Okay. Okay. So for this random variable t, property 2 says since the equation holds above, since the equation this equation, since the equation star holds above, that t is an exponential random variable. Okay, this weird statement that I colored in here holds, and so t is an exponential random variable by property 2. Okay, so t is an exponential random variable. That means that we know the probability density function of this random variable. So as an exponential random variable, we know that the PDF of t is little f of t is equal to 1 divided by theta e raised to the negative theta negative t over theta. Okay, it's of this form from here. Okay, and so this is for x positive. Okay, so it has that form. Our variable is t instead of x. So it's going to be t. So that's the PDF for an exponential random variable. So given this sentence, we know the property 2 holds, which implies that you have an exponential random variable. And that means that the PDF of your random variable has that form. Now we're just going to use this PDF function to find the probability we want. Okay? But you're given this probability. That the probability of t is greater than or equal to 10 is 0.99. So that means that since the probability that t is greater than or equal to 10 is equal to 0.99, then this is equal to the integral from 10 to infinity of your PDF function, which is 1 over theta e raised to the negative t divided by theta dt. Okay, but you don't know what theta is. And so, but you do know that this integral is equal to 0.99. Theta is a constant. And so I'm going to move the theta out of the integral. So I have 1 over theta. And I want to calculate an you want to use u substitution to find this integral, where theta is just a constant that you don't know. So, okay, so using u substitution and letting u equal to negative t divided by theta, we get that the u is equal to negative 1 divided by theta dt, and that the integral, this integral, is equal to the integral of, well, you have a negative 1 over theta d theta. Here's only 1 over theta d theta. So I'm going to multiply the outside by negative 1 and the inside by negative 1 also. And so then you get negative 1 dt. Okay. So now, and this is still 10 to infinity. And so, and this is, you have the 1 over theta here. Okay, if this is 1 over theta, I'm just putting here. So we have a negative 1 over theta d theta here. That's the u. The negative t over theta is u. And so by u substitution, this is equal to the negative 1 times this integral, which is e raised to the u du. And if t is 10, then u is negative 10 divided by theta. If t is infinity, then negative infinity over theta is negative infinity. Okay. So now you just compute this integral. So an antiderivative of e to the u is e to the u. You have a negative 1 in front. So e to the u is an antiderivative of e to the u. You're evaluating it from the lower limit, which is negative 10 divided by theta, to negative infinity. Okay. So this is equal to negative 1 times e raised to the negative infinity minus e raised to the negative 10 divided by theta. Okay, so this is equal to negative 1 times e to negative infinity is 0. And it's minus e raised to the negative 10 divided by theta. And so now the negative 1, 0 is gone. So negative 1 times negative e negative 10 over theta is e raised to the negative 10 divided by theta. There you go. So this integral is equal to this. Okay, so I'm going to call this double star. And I'm going to say that this thing, because this is equal to this, now this is equal to that by double star. Okay, so the probability that t is greater or equal to 10 is given as 0.99, and it's equal to this integral, which we calculated was this. So we know that 0.99 is equal to e to the negative 10 over theta. So we know that 0.99 is equal to e to the negative 10 over theta. And now we solve the theta. Okay, and when we solve for theta, then that means that we found now the specific exponential function for t. We find its PDF. All right, well, if you take ln of both sides, you get ln of 0.99 is equal to ln of the right side. Well, ln of the right side is e, ln of e raised to the negative 10 over theta. Ln and e cancel because they're inverse functions, and so you get negative 10 divided by theta. And it's ln of 0.99. And then, so taking ln of both sides, you get that. Then solving algebraically for theta, you get that theta is equal to negative 10 divided by ln of 0.99. Okay, now when you calculate that value, negative 10 over ln of 0.99, you get equal 994.99. Okay, now that we have found theta, we know the PDF of our random variable capital T, because we only knew this much about it. We know the PDF of capital T is this, except where theta is equal to 994.99. So now we substitute that value of theta in here, and we now know specifically what the parameter is of our exponential random variable. It's 994.99. We got that from the given probability. The probability that t is greater than 10 is 0.99. So now that we know the PDF function, we can calculate probabilities of our random variable t. And so again, the goal is to find the probability that t is greater than 100. With the PDF of t, we can now do that. So, okay, so with the PDF of capital T, we can compute the probability that t is greater to 100. Okay, so the probability, so you integrate. So the probability that t is greater or equal to 100 is equal to the integral from 100 to infinity. From 100 to infinity of this PDF function, dt. Right? And so this is still just using u substitution. Okay, so using u substitution, where u is equal to the exponent. For these examples, not every example you would use the exponent. So one way to do it, where u equals negative t over 994.99, we get du is equal to negative 1 divided by 994.99 dt, and that this integral is equal to the integral, well, you have an e to negative t over 94.9. You have 1 over this, you have this fraction dt. You want the negative of it. So just like the other examples, you multiply the inside and outside by negative 1. And so before you do the u substitution, you just make everything easy. You set everything up. So you have the 1 divided by 994.99 here. We multiply the outside by negative 1, so you multiply the inside by negative 1 as dt. So this negative, the fraction dt, that's du. And negative t over 94.99, 994.99, that's the exponent. So this is equal to negative 1 times the integral of e to the u, du. E to the u, du. And the negative 1 is in front. But if t is 100, then u is negative 100 over 994.99. If t is infinity, then negative t over 994.99 is negative infinity. So this becomes a negative infinity here. This is equal to negative 1 times an antiderivative of e to the u is itself e to the u. You're valuing from the lower limit, which is negative 100 divided by 994.99. So it's from that to the upper limit, which is negative infinity. Okay, so you have negative 1 times e to the negative infinity minus e raised to negative 100 divided by 994.99. And so this is equal to negative 1 times e negative infinity is 0. 0 minus e raised to the negative 100 divided by 994.99. Right, and that's equal to the negatives cancel. 0's gone, it's negative of that, and so you end up with this. Okay, so this integral is equal to e to negative 100 over 994.99. Okay, and so we'll call this triple star. And so we have from triple star that this integral is equal to e to negative 100 over 994.99. This is by triple star. All right. And so we now calculate the probability t is greater or equal to 100. It's e to negative 100 over 994.99. And as a decimal, this is equal to 0.904. Okay, fact, if the waiting time between events of a specific kind is an exponential random variable with parameter theta. The number of this kind from time 0 to time t is a Poisson random variable with parameter lambda t, which is equal to 1 divided by theta t. Okay, so another example is example 5.14. So let me just put up this previous example from the last lesson. Okay, so in the last 19. Okay, so from last lesson, we did an example. We did an example 5.11. Okay, so that example is this one. The time interval in minutes between calls arriving is an exponential random variable with parameter theta equals 0.5. And then we answered questions about it. Okay. So here, it says from that example, what is the probability that more than 3 calls arrive within a 5-minute period? Okay, so from this fact, we get this answer. So the fact says if the waiting time of a specific kind, if the waiting time between events of a specific kind is an exponential random variable with parameter theta. So if this happens, and this example says the time interval in minutes between calls arriving is an exponential random variable with parameter theta equals 0.5. Okay, so that's happening in this problem. We're waiting. The wait time is an exponential random variable with parameter theta. If the wait time is an exponential random variable with parameter theta, then the number of this kind from time t equals 0 to time t is a Poisson random variable parameter theta t. Lambda t equals 1 over theta t. Okay, so we now have this conclusion. Okay, so since the assumption of the fact above applies to this example, we first conclude that the number of calls arriving from time t equals 0, from time 0 to time t, is a Poisson random variable with parameter lambda t, which equals to 1 over theta t. Okay, So the conclusion of this fact is that since we have the purple statement is true, then we conclude that the number of calls arriving from time 0 to time t is a Poisson random variable parameter lambda t equals 1 over theta t. Okay, so now with that conclusion, our PDF function, we now know our PDF function. So this means that so let me just so let me add to this. Let capital X equal the number of calls arriving within a 5-minute period. Okay, so we know that capital X is a Poisson random variable with parameter lambda t, which is equal to 1 over theta t. Okay, and so this means that the probability of more than 3 calls in a 5-minute period is equal to the probability that the number of calls is greater than 3, x is greater than 3. And so this is equal to 1 minus the probability that x is less or equal to 3. And this is equal to 1 minus the probability. So the probability that x is less or equal to 3 is the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. Okay, and so this is equal to 1 minus, well, x is a Poisson random variable, and so notation for that is little p of 0 comma lambda. Okay, where okay, 0 comma lambda, and then plus little p of 1 comma lambda plus the probability plus p of 2 comma lambda plus p of 3 comma lambda. Okay, so lambda is equal to 1 divided by theta times t. Okay, so then this is equal to 1 divided by theta, which is given as 0.5 times t, which is 5, because it's a 5-minute period. Okay, so the fact that it's a 5-minute period means that t is 5. Okay, so that's where we're getting the number 5 from. So that might be hard to see. Maybe I should use a different color. I'm trying to use a color I didn't use before. I'm running out of colors. Okay, here's a weird color. So let's go with that. Okay, so that's 1 over half, which is 2 times 5. This is 10. Okay, so lambda is 10. And so that's equal to 1 minus the sum p of 0 comma 10 plus p of 1 comma 10 plus p of 2 comma 10 plus p of 3 comma 10. So this is equal to 1 minus, and then you find the value of each of them. Okay, so then, so when you, so you have x comma lambda, which is equal to, equals to 1 over, 1 over lambda t to the okay, so it's okay, so then it's equal to, it's equal to x factorial in the denominator, lambda t raised to the x e to the negative lambda t. Okay. It's lambda e to negative lambda. There we go. Okay, so then, okay, so you plug this in, so then you get p of 0, comma 10 is equal to, so you have 0 factorial in the denominator, you have lambda, which is 10 to the 0 power, e raised to negative 10. And so then this is equal to e raised to negative 10. Okay, and then you complete the other one similarly. So p of 1 comma 10 is equal to, you have 1 in the factorial in the denominator, you have 10 to the first, e raised to negative 10. Okay, so this is equal to 10 e raised to negative 10, and so forth. And so then you use your calculator and you plug them in. I guess since everybody started this, I'll keep going. So then p of 2 comma 10 is equal to, the numerator is 2 factorial, the numerator is 10 squared, e raised to negative 10. So that's equal to 50 e raised to the negative 10. And this is row of 4 comma 10, which is equal to, the denominator is 4 factorial, the numerator is 10 to the 4th power e to the negative 10. And so then that's equal to, 10,000 divided by 24 e raised to the negative 10. Okay, and so you add up all 4 of these things and you plug them in there. And so 1 minus that sum, and you get 1 minus 0.0104. And this is equal to 0.9896. Okay, so you just add up these 4 from here, and you plug in that sum value there. 1 minus that sum is that. Okay, it's side note, so then we'll take that into effect. Okay. I don't want to do 4-star or 5-star. Okay, so okay, so one more note, and then we're going to the section. So if there are an average, if there are on average lambda events of a specific type within a unit time interval, then on average, the time between events is theta equals 1 divided by lambda. Okay. So in other words, if capital X is an exponential random variable with parameter theta, then on average, the observed value of capital X will be theta. So for example, if the time in minutes until an accident after 4:30 p.m. is an exponential random variable with parameter theta equals 15, then on average, that time is 15 minutes. Okay, so if the time in minutes until another accident after this 4:30 p.m. is an exponential random variable with parameter theta, then on average, the time in minutes you have to wait is theta, 15 minutes. Okay, so that annoying section is over. And so next class, so that's the end of that section. Okay, so next class, we will discuss the normal distribution. Okay, which is probably the most important distribution in probability. Okay, so give me 1 second. Just want to check the homework. Okay, so there's no homework for next class. Okay, so we can stop here. It's 7:45. So the lesson's over. I don't think I used the whiteboard at all. I didn't, so I don't have to save it. Are there any questions at all?
No question.
No? Okay, so that's it. Okay, so have a good night.
I
And
have
I'll see all of you on Thursday.
a question.
Okay, yeah.
So, did you set it the next exam? The day of the next exam, like
So, okay, so I think I'm going to announce it. Thanksgiving break is Thanksgiving's the 25th, right?
yeah.
Okay, so I was going to announce it next class, but if you want me to announce it now, I can. So okay, so there's only 2 tests in this class, so it's going to be after the break, right? Actually, let me announce it next class. I'm not going to announce it now, okay?
Okay.
It's going to be after the break. There's only 2 exams. So the second exam will be right before the final. Okay.
Mm.
So it's almost at the end of the semester, almost the end. Okay. It'll be after the break though. Okay.
Okay.
We can talk more about it next class on Thursday,
Okay.
but it will not be until after the break.
Okay.
Okay. All right. Have a
Okay.
good night.